There is a metal that, for more than 100 years, humanity could only look at from a distance. Not because it was rare, not because it was buried deep underground like some cursed treasure, but because every time we tried to touch it, it would immediately betray us and turn into something as brittle as an overbaked cookie. It sounds a bit dramatic, but that is exactly the story of titanium, an element discovered in the late 18th century, sitting calmly in the periodic table, almost as if it were looking back at us and saying, "Go ahead, try." And we did try. For more than a century. The result? Failure after failure. So the question is, why was a metal that existed right in front of us almost impossible to actually obtain? And why, to tame it, did humanity have to build an entire industrial ecosystem just to satisfy an element that is deeply obsessed with oxygen? The story does not begin in a modern laboratory, but at the end of the 18th century, where things seemed far simpler than they really were. In 1791, an English clergyman named William Gregor discovered something unusual in black sand in Cornwall. He analyzed it and realized it contained an element that had never been described before. A few years later, the chemist Martin Heinrich Klaproth named it titanium, drawing inspiration from the Titans of Greek mythology, giant beings of immense strength, nearly impossible to defeat. The name alone already sounded dangerous. But at that time, titanium existed only on paper. Scientists had its compounds. They knew it was present in ores. Yet every attempt to isolate it as a pure metal resulted in something hard, brittle, and fragile. Not a workable metal that could be forged, drawn, or shaped. Imagine discovering gold. But every time you melt it, it turns into glass. The feeling would probably be similar. Throughout the 19th century, chemists kept experimenting. They used carbon for reduction, just as in iron production. They increased temperatures. They altered reaction environments. But titanium seemed to have a peculiar habit. It always managed to bond with oxygen before anyone could separate it. And once titanium joined hands with oxygen, that relationship was incredibly stable. We knew it was there. But we could not keep it for ourselves. It was like a ghost in the periodic table, clearly present, yet impossible to grasp. What made it so difficult? The answer lies in a chemical personality that borders on obsession. Titanium is not rare. In fact, it is the 9th most abundant element in Earth's crust. If Earth were a giant pizza, titanium would make up about 0.6% of the crust, meaning that in every 100 slices, nearly one contains it. Not exactly something impossibly scarce. The problem is not quantity. The problem is that it loves oxygen too much. At high temperatures, titanium reacts with oxygen almost frantically. It also reacts with nitrogen, carbon, and even hydrogen. But oxygen is its greatest attraction. When heated, titanium will steal oxygen from anywhere. From the air, from furnace walls, even from the materials containing it. The result is titanium dioxide, a white, stable, extremely durable compound. The very substance you are likely applying to your skin as sunscreen, or seeing in white paint on walls today. Sound familiar? That is the paradox. We use titanium compounds everywhere. Yet for more than 100 years after its discovery, almost no one had access to pure titanium metal itself. Because to remove oxygen from titanium, you need a reaction that is stronger, faster, and takes place in an environment almost completely free of oxygen. And in the 19th century, the idea of a truly oxygen-free environment was nearly impossible. Metallurgical furnaces back then were like giant kitchens, full of air, burning coal, and open reactions. And every time titanium was introduced, it would immediately turn and embrace oxygen as if it were destiny. Scientists began to realize an uncomfortable truth. The challenge was not finding titanium. It was isolating it from the entire world. It sounded almost like a forbidden love story. And it was not until the 1930s that someone dared to think completely differently. William J. Kroll was not the first to attempt titanium extraction. But he was the first to accept a difficult truth. You cannot process titanium like iron. You have to isolate it. Imagine trying to separate two people deeply in love, who keep finding their way back to each other. The only solution is to lock them in separate rooms, seal the doors, and cut off all contact. Kroll did exactly that. Instead of heating titanium ore directly, he converted it into titanium tetrachloride, a volatile liquid. Then, inside a completely sealed furnace, he reacted it with magnesium metal at temperatures around 800 to 1000 degrees Celsius, odd enough to make steel glow red. Most importantly, the environment contained almost no oxygen, typically filled with inert gases like argon. Magnesium acted like an oxygen thief. It has a strong affinity for chlorine and oxygen, willingly pulling them away from titanium. When the reaction finished, what remained was metallic titanium in a porous form known as titanium sponge. Not a shiny ingot, not a mythical blade, just a gray, spongy mass. But for the first time in history, humanity truly held pure titanium in significant quantities. This process, known as the Kroll process, sounds cumbersome, and it is. It consumes enormous energy, requires sealed furnaces, inert gases, and highly purified magnesium. And if oxygen sneaks in at any point, the entire batch can fail. Dangerous, expensive, complex, but it works. And here is the interesting part. Nearly a century later, we are still using almost the same method. Why has a world with spacecraft and supercomputers not found a cheaper way to tame titanium? The answer lies in the true cost of its stubborn nature. When people hear titanium, they think of aircraft, spacecraft, medical implants. It has an extremely high strength-to-weight ratio, about 45% lighter than steel, yet comparable, or even superior, in strength for many applications. It resists corrosion exceptionally well. Even the human body accepts it, with minimal rejection. It sounds like the perfect metal, but perfection always comes with a bill. Titanium is not expensive because it is buried deep underground. It is expensive because producing a clean bar of titanium requires building an entire production chain. That resembles a complex ritual. Mining the ore, converting it into titanium tetrachloride, refining it, reacting it with magnesium in sealed furnaces, removing magnesium chloride, then remelting it in a vacuum to eliminate impurities. Every step can fail if oxygen interferes, and every step consumes enormous energy. Imagine maintaining temperatures near 1000 degrees Celsius. Inside, a sealed system filled with purified inert gas. That is not a household stove. That is an industrial facility with massive operating costs. So when you see a titanium watch or a titanium bicycle frame priced far higher than steel, you are not just paying for the material. You are paying for an entire ecosystem built to satisfy an element that loves oxygen a little too much. And the irony is this. Even after we have tamed it, we still have to respect its rules. A small mistake during welding or casting, and titanium can absorb oxygen again, becoming brittle once more. It has never truly been easy to work with. So every time an aircraft takes off carrying tons of titanium in its structure, it is not just a triumph of engineering, it is a triumph of persistence. One that took more than 150 years. The next time you hear someone say, "Titanium is expensive," you might smile and think, It is not expensive because it is rare. It is expensive because it forced humanity to struggle for over a century just to touch it without being betrayed. Picture that for a moment. For 150 years, scientists saw its name in the periodic table, understood its theoretical properties. Yet every trip into the furnace ended in failure. Like holding a key while the lock keeps changing shape right in front of you. And only when we accepted the need to build a completely sealed environment, tailored to its personality, did titanium finally cooperate, seen this way. Every titanium bolt in an aircraft, every artificial hip joint in someone's body, is the result of a century-long intellectual battle between humans and an element that is deeply loyal to oxygen. If you enjoy stories like this, where science is not just formulas but drama, personality, and silent battles between humans and nature, there are many more fascinating characters waiting to be told. There is an element that was once considered useless, nearly discarded, only to become the heart of the entire modern electronic world. Sounds a little familiar, doesn't it? We will open that door next time.